Good morning, everyone. Today, I will present our work entitled Development and Experimental Evaluation of a Vibration-Based Adhesion System for Miniature Wall Climbing Robots. This work was conducted at the University of Nottingham within the University Technology Center in Manufacturing and On-Wing Technology. I am Sichuan Li, and it's my pleasure to share the motivation, design, experiments, and conclusions of our study. Wall climbing robots have become increasingly important in industrial inspection, infrastructure maintenance, and in situ repair, where human access is difficult or unsafe. However, the key challenge lies in achieving stable and controllable adhesion while keeping the system compact and energy efficient. Existing adhesion methods such as suction, magnetic, electrostatic, or bio-inspired adhesives each have specific limitations. Suction requires bulky pumps. Magnetic adhesion only works on ferromagnetic surfaces, and electrostatic systems are weak and release slowly. Therefore, we aim to develop a new adhesion approach that combines strength, speed, and simplicity. And next, comparison of adhesion methods. This table summarizes traditional adhesion techniques. You can see that none of them perform well across all key criteria: payload, roughness, adaptability, reliability, and energy efficiency. This gap in performance motivated us to explore a new vibration-based adhesion mechanism, or a VBA, which could potentially overcome many of these trade-offs. Our proposed system is based on a flexible PET disc, driven by an eccentric rotating mass motor, the EMRM. When the disc vibrates near a surface, it forms a thin air film that produces a controllable attractive force without a direct contact. By simply adjusting the vibration frequency, the robot can switch between adhesion and detachment almost instantly. The advantages are clear. It's non-contact, avoiding surface wear or contamination, fast switching with no mechanical valves, a high adhesion to weight ratio exceeding 51 times, and very low shear resistance, ideal for high-speed motion. And let's look at the system structure. The main components include an ERM motor with an eccentric mass as the vibration source, a PET film disc with a 7 cm radius and a 1 mm thickness, and mounting adapters made of acrylic and aluminum. The design ensures that the motor's vibrations are efficiently transferred to the flexible disc, allowing a uniform oscillation close to the surface. To evaluate the system, we built a serious experimental setup and performed a series of frequency sweep experiments from 100 to 200 Hz. We measured both the adhesion force and the centrifugal force using a load cell, while monitoring the motor through a data acquisition system implanted in LabVIEW. The key observation was that below 140 Hz, adhesion was almost negligible, but above that threshold, adhesion increased significantly and linearly with frequency. And next, look at the results of adhesion and centrifugal force. This figure shows the results of our measurements. The left curve represents adhesion force, which begins to rise sharply once the frequency exceeds about 140 Hz. The right figure shows the centrifugal force generated by the motor, which also increases with frequency and exceeds 1 Newton at higher speeds. Together, these results indicate that higher vibration frequency not only increases the dynamic pressure in the air film, but also strengthens the overall adhesion effect. From these experiments, several key findings emerged. Firstly, the system structure is feasible and able to lift light objects using vibration alone. Secondly, the adhesion force versus frequency relationship is nearly linear beyond 140 Hz, which shows good controllability. At last, the system demonstrates clear advantages over traditional adhesion methods in compactness, responsiveness, and energy efficiency. These properties make the VBA system an attractive option for miniature wall climbing robots that need fast and reversible adhesion. While our current prototype proves the concept, several improvements are planned. The first one is to integrate closed-loop control and precise sensors to better regulate vibration amplitude and frequency. The second, testing the system in multi-environment to see its adaptability, including different surface materials and roughness. And the third one, optimizing energy consumption and durability for long-term applications. Ultimately, we hope to apply this technology to non-destructive testing and autonomous inspection robots. To summarize, this research demonstrates a novel vibration-based adhesion mechanism that enables strong, controllable, and fast switching adhesion without contact. It opens up new possibilities for small wall climbing robots and other systems that require reliable surface attachments. And thank you for your attention. I'd be happy to take any questions.